Question 10's got a mixture of topics in it. The first one is saying that this wire transmits electromagnetic waves when an alternating potential is applied at one end of it. Now that's probably a situation you're not really familiar with, but it doesn't matter because all the information given. It doesn't matter because all the information you need is given in the question. So for the first part, the wavelength of the radiation transmitted from the wire is twice the length of the copper wire. That's the only information you need really. So if the wire is 38 metres long, the wavelength of the radiation is going to be double that. You work out what it is. Calculate the frequency of the transmitted radiation. So we've got information, we now know the wavelength, we're trying to find the frequency. So hopefully you remember the GCSE equation that links frequency, wavelength and speed. What we're not told in this question is we're not told the speed of the waves. And you might think that you don't know the speed of radio waves, but of course you do. They're electromagnetic waves. All electromagnetic waves travel at the same speed. And that speed is given on your datasheet. You might know it, of course, as the speed of light. Part B comes to a completely different topic. It's to do with forces and equilibrium. It's also rather a dodgy question, this, because in order for you to be able to work this question out and to do it the way that the mark scheme's done it, you actually assume that these two masts aren't fastened to the ground. In reality, you've got vertical masts anchored to the ground. You can have any force you want in the cable between them, so as it doesn't pull them over. I thought it looked a bit dodgy, so I checked the mark scheme, and sure enough, the mark scheme is actually assuming that these masts are just sort of balanced there and could fall over. It's a bit of a strange question, but never mind. So the first part, it's connected with just resolving forces. There's a tension in this cable, which of course is pulling partly down and partly across. So the downward part would just be pushing the mast into the ground. That's not a problem because the ground is holding it up. The across part will be making the mast try to topple that way, but the mast doesn't topple that way because it's held in place by this copper wire. So all you've got to do is you've got to find the component of this force that is acting horizontally. Now usually when we've got questions to do with components, we're usually given the angle. In this case you're not given the angle, but you're given enough information. We want to find this angle here. You know that side, which is the opposite, and you know the hypotenuse, so you can find the angle. Then when you've found the angle, you've got to, let's just draw one a little arrow there. That's the tension in the wire. You've got to find the horizontal component of that tension. And we know it's going to either have sine theta in it or cos theta. You've got to choose the right one. Remember the trick for choosing the right one? Ask yourself, with those dimensions, is that force going to be mainly downwards with a big vertical component and a small horizontal component, or is it going to be mainly across with a big horizontal component and a small vertical component? You sort that one out. Whatever you get as a horizontal component, that's balancing the tension in the wire. Next part, it tells you the diameter of the wire. Calculate the stress in the copper wire. So hopefully you know the formula for stress. It's something you do need to learn. Force divided by area. Just remember to get the right units. The diameter is given in millimetres. If we're going to give the stress in newtons per square metre, you've got to do a conversion. And of course, the number of square millimetres in a square metre is not 1,000. The thing to do, of course, is always check when you've got answers that when you're working out areas, are you given the diameter or given the radius, and don't get them mixed up. The last part, a discuss question. That means they're not really looking for a correct answer, they're looking for you saying sensible things. Discuss whether the wire is in danger of breaking if it is stretched further due to movement of the top of the mass in strong winds. And it tells you what the breaking stress of copper is. So when you're going to discuss that, you've got to take into consideration the values you've got. So you've already worked out the stress in the copper wire. If the answer you get for that stress there is close to the breaking stress, then I think it would be reasonable to suppose that a bit of wind might cause the wire to stretch a little bit and take you above the breaking stress. But if the answer you've got for this part is nowhere near, like it's less than 1/10 of the breaking stress for instance, I think we could assume that those cables can flap around quite a bit without taking you above the breaking stress. So that's the sort of thing to take into account. We've also got to remember, of course, that copper is a very ductile material. So long before it gets the breaking stress, it would deform plastically. So that might affect your decision about whether or not the wire would snap. So I forgot that. There are 2 marks available, so you should say 2 sensible points. But to look at the actual mark scheme for that, if you go to Caboodle, the Unit 2 end of unit tests, to check the mark scheme for this, to look at some of the points that you could mention, if you go to the Caboodle website, the Unit 2 end of unit exam questions, there's a work solution for that lists loads of points that you could mention 2 of. So question 11. So the diagram, it says it's an arrangement used to investigate the properties of microwaves. And we've done this experiment in college. So you've got a transmitter and receiver. When you rotate the transmitter through 90 degrees, so sort of turning it round that way, and this is an experiment we have done in college. If you rotate the transmitter about the axis through 90 degrees, so it's still pointing towards R, but you just spin it about the axis, the signal that you receive decreases to 0. So what's that effect called? We've done experiments in it. Did it with the microwaves. We also did experiments with little bits of plastic to show the same effect with light. So you need to know what that effect is called, and then explain how it happens. In other words, what does it mean? What's the nature of the microwaves that mean that effect will happen? Part B. A microwave oven produces microwaves of wavelength 0.12 meters in air. Calculate the frequency of these microwaves. So we've got information about wavelength, we want in frequency. We obviously need to use the equation that links those two. And of course that equation has speed in it. Do we know the speed of microwaves? Well, they're electromagnetic waves. The same sort of waves that light waves are. So therefore your datasheet ought to tell you what the speed of waves like that is. The last part of this question, in a certain oven, explain why food heated in a fixed position in the oven would be uncooked at certain points if stationary waves were allowed to form. So think what you know about stationary waves. You've seen them on a string. What's the special feature of stationary waves? To do with energy. Remember, the whole point of a microwave oven is to get energy into the food. When you've seen stationary waves on strings, is there energy transferred at every point on the string, or are there some points where there's no vibration and therefore no energy? If that's the case for waves on a string, it would also be the same for standing waves in microwaves. So use that idea to explain why, if you've got standing waves, there could be certain parts of the food that don't get cooked.